So I want to talk about this result called Bogomolov instability. So, you know, this is really a result for rank 2 vector bundles on a surface. Or you can, of course, do higher rank vector bundles on a surface or higher rank vector bundles on higher dimensional variety. But what I really want is rank 2 vector bundle E over S, a surface, and there's a result saying that C1 squared less than or equal to 4C2. This is of E x unless, and then some very strong consequence. So I want to explain that this is a kind of primary result. This is, you know, like the index theorem that you get directly out of the form of Riemann-Roch theorem. And later on, like, you know, the results for minimal models of surfaces that likewise come out just out of the shape of Riemann-Roch. So this is really a very, very coarse result. And I want to explain it in very, very simple terms. So there's only one place here where there's, you know, a slightly tricky argument. Okay, and let me, so this is a, you know, very simple argument, has very strong consequences. And it's sort of slightly mysterious that it works for surfaces and it doesn't really work for high dimensional varieties. So first of all, let me explain what I mean by, so let me have B a base scheme. So it's a scheme over a field K. I'm only doing things relative over a field K. Right, and this will sometimes be a surface, but it'll also sometimes be a curve or sometimes a high dimensional variety. So don't make any assumptions about it. So E, a rank 2 locally free sheaf. So locally free means that you know, if I take a suitable open set, a suitable open neighbourhood of any point of B, then E restricted to U is O plus O. Well, this means that I can find S1, S2 in sections of over U of the sheaf E, so that E is, let me call these X1, X2, so that E is X1, X2. So, sorry, E is OX1 direct sum OX2. And this is just an isomorphism of E with O plus O. Okay, so if I do this, then I can make the symmetric algebra of E. Right, so this is O direct sum E direct sum sim 2E direct sum, and so on. So somewhere here there's sim NE. So you know, I'm assuming you can figure out what sim NE is. It's E tensor divided out by symmetrizing, right? But in any case, so if I do this construction restricted to U, restricted to this place where E is just X1, X2, this is the polynomial algebra OB. So, of course, restricted to U of X1, X2. Right? So this is exactly what sim2 of E means. sim2 of E means I take a basis X1, X2, and I write down X1 squared, X1, X2, X2 squared, and I make them to be basis of a vector bundle. Right? So this is just a definition. The sim of E is this expression, which is written like this. And the good thing about this is that it's intrinsic. It doesn't depend on having a basis or anything. Whereas here, this depends on a basis, and you can understand exactly what it is. Right? So if I do this, then I can take spec of this sim E. And this is sort of something like hard E, or something over B. So this is locally A2 with coordinates x1, x2 times B. So I said I'm thinking of everything of the B as being a field over K. So I don't have to worry about absolute product here. This is a fiber product in the language of scheme theory over the scheme X, right? And you know, there's a little thing NB, because you know, this is I'm doing algebraic geometry. So when I think A2 x1 x2, this is x1 x2 are linear forms on B, on E, right? So this is a Grothendieck language, and you know, topologists would usually prefer to use the dual notation, where this having x1, x2 in E is actually a point. Each of x1 is a section of E. So here, these x1, x2 are not sections of E; they're linear forms on E. You know, each time you use a vector bundle, you have to be aware that there is the language preferred by you know, students of Grothendieck, scheme theorists, and there's a language preferred by topologists, and there's a kind of little duality. So, you know, if you want to write E dual, if you prefer, right? But I'm not taking any responsibility for what happens when you do that. So this is just a trivial little point that you have to decide at the beginning which you're going to do. Right? And in exactly the same way, there's proj of sim E. So this guy here is an algebra, but he's also a graded algebra. Here has graded pieces. A graded piece of degree n is like this. And this is P of E, right, over B. And this is locally in the same open sets, P1 of with homogeneous coordinates x1, x2 times B. Okay, so this is, you know, this is just, I'm sure everybody here knows this and has seen this, but I'm just trying to set out the notation. Right, so this is a proj. So proj carries, always carries, tautological sheaves OX of you know, any degree A. But here OX of 1 is a line bundle. Sorry, it's not OX, it's OP E of 1. It's a line bundle on P of E. It's on every fiber P1. It's O P1 of 1. Right, but the thing that sort of distinguishes this is that over U, if I take global sections of this OPE of 1 over, so you know this, we probably need some name for this, so let's call this pi. Right, if I take pi lower star, if I take pi to the minus 1 of the open set U, this is OU of, so this is x1, x2. Right? And so in other words, just saying this for all open sets U is just the same thing as saying that pi lower star of OP1 is pi lower star of OP. Pi lower star OPE of 1 is E. Right. So the sections of this over an open set, the sections of pi lower star of this over an open set is functions on the base times x1 plus functions on the base times x2. It's just sections of this sheaf. Okay, and if I do pi lower star of OPE of this guy here with a weight A, OPE of A, this is sim A. Right, so this is just the definition of a proj. When you do proj, this is the tautological information you get. Yeah. So I want to specialize to the case. Now let's take the base B equals C non-singular curve. Non-singular projective curve. Okay, so maybe it could be a singular curve as well. I don't think it makes any difference. So then the picture is sort of like this. So I'm going to write P of E. I'm going to write P of this E is now, I'm going to write FC. So F is for surface. And it looks like this. So here's A, the fibre, which is P1. Right, and here's the base C. And so I want to know lots of things. I want to be able to do, in particular, intersection theory on this. And I want to know intersection numbers. So, you know, this is still, so now this is related to E, a rank 2 vector bundle on C. Okay, so everybody's seen this picture before. So what do I want to say about this? So so this is a lemma or proposition. I mean, I'm just assembling all the trivial things you can say about this construction. So pick of FC is pi lower star pick of C, direct sum Z times this O of 1. Right. So the only way, the way to, you know, this will be true for a vector bundle of higher rank as well. I mean, it's easy, but and the canonical class of FC is O of minus 2. So it's supposed to be O of minus 2 on each fibre, and then tensor. So this is the P of E. Right. So this is a sheaf on the proj which obtains in this way. So, you know, it doesn't have any global sections because it's negative, but it's still a perfectly well-defined sheaf. It looks locally like forms of degree d minus 2 divided by forms of degree 2. Yes? Tensor determinant of E. Tensor KC. Now, where does the KC go? And, you know, the dual of this statement is the tangent bundle. So now I'm going to write down relative, tangent bundle relative of the P of E over C. So, you know, when I wrote down the formula for the canonical class, and of course I could take this canonical class and put him over there. So, you know, this would give a formula for K of FC over C, the relative canonical bundle. Right, and that just takes this and puts him over there. So I'm doing the dual of that formula. And this is OPE of 2 tensor this pi upper star of the determinant of E to the minus 1. Okay, and this bundle I'm going to be coming back to later quite a lot. This is called B. Right, so this is the Bogomolov discriminants. Okay, and when I do this construction, so you know, I mean, if you want to number these, you know, this is sort of, I don't know, 1, 2, 3. If L is the divisor class of O of 1, so I've told you what pick is. Remember, pick is divisors up to linear equivalence. I can also take divisors up to numerical equivalence, and I get n1. So this is, you know, the divisors up to linear equivalence, or it's the Nirol-Severi group, if you prefer. Then n1 of fc, so n1 of this surface, is z of a and L, with a squared equals 0. A is the fibre. So, you know, one fibre there meets another fibre there in no points at all. A times L equals 1. So the L is O of 1 on each fibre. Right, and L squared equals the degree of E. Right, so the degree, this means the degree of the vector bundle E over C. We'll come back to this later. It's the same thing as the first Chern class of E in H2 C Z. So what do I have to prove? I mean, you know, these are sort of basically easy things. If you know, if M any line bundle on f of C, right, then M restricted to the general fibre A is OP1 of some degree D, and so then I can do M tensor O of minus D, right? So this is OPE, right? I own, by construction here, I own a line bundle which is O of 1 on the general fibre. So if I see a vector bundle which is D on the general fibre, then I subtract off D copies there. And so this is, you know, this is degree 0 on the general fibre. And, you know, you can find out quite easily this is pullback of some, you know, L naught or something. L naught in P. C. So I don't know if you can do this completely in a completely elementary way. You know, what I really want to say is consider the functor pi lower star. Then, you know, this is a sheaf on the surface FC, and I want to push it down. And so there is a kind of method of pushing down a sheath by restricting it to every line and then pushing it down, restricting it to every fibre. That's called the base change theorem. So here the fibres are one-dimensional, so R2 F lower star is 0, and then you can calculate R1 F lower star fibre by fibre. So this guy is 0 on each fibre is P1, so there's no R1 F lower star there. And then pi lower star you can also calculate by fibre by fibre. So pi lower, so you know, I mean, I'm sorry, this is, you know, at some point you have to pay the price. But completely, this is the most trivial case of the base change, the coherent base change theorem, the base change theory in coherent cohomology, which you're supposed to eventually come to terms with. Pi lower star of this is something that you can calculate fibre by fibre. So on each fibre this is P1, and this is just the sections of the line bundle of degree 0 on each fibre. So this is L naught. This is locally aligned bundle. Right, and then, you know, you can do pi upper star of, you can mess around. You can say projection formula if you like at this point. But, you know, I mean, this is, the argument's very easy. Anyway, this is just to prove this thing. If I take any line bundle here, then after subtracting off a little multiple of the O of 1, I get something which is in the pi per star there. Right, so how do I get the canonical class? How do I do this? So the canonical class is certainly, whatever else it is, it's certainly some line bundle on PIC. It's certainly some element here. So I can certainly write the sum multiple here times some pullback of some bundle. Right? It's certainly got degree -2 on the fibre, so there's no, so K of FC tensor O of 2 is certainly of the form pi per star of some line bundle. And you just have to figure out what that line bundle is. Now, why should it be Kc tends to the determinant of E? So at least you notice here that this expression, the expression is O of -2 tensor determinant of E tensor Kc. Right, is independent of is left unchanged by doing E maps to E tensor some L, right? Because this of course changes the E, so because then determinant of E is changed to E tensor L squared, just automatically. I'm multiplying all the elements in a matrix by 2, but the O of 1 maps to O of 1 tensor L. Right, because if you thought about these formulas I had here with E being locally OX1 plus OX2, then if I change the E by doing this, I'm just tensoring this by L, right? And that has the effect of just changing the tautological sheaf O of 1, the sheaf where x1 and x2 live, by tensoring it by L. Okay, so what else do I have to say? Well, you know, if I'm on a little piece of the curve here B, if I'm on a piece of the base curve C and I've got a local parameter, then here, you know, I've got a little piece of the surface FC, and I've got a parameter in this direction which is x1 over x2, and here I've got a t which is a parameter over the base. So you know, the k of FC is d x1 over x2 wedge dt, and you know, it's this. I mean, let me not try to. I'll probably make it even less convincing if I try to explain it any further. Okay. So what else do I want to say? How do I calculate these intersection numbers? Well, I mean, these are completely trivial. So this L squared equals degree of E is basically the definition of degree. Right. So if you look at Grothendieck's definition, I'll say this in a complicated way first, and then say it in a simple way. Grothendieck's definition of Chern classes says, well, if I've got P of E over any base X, right? So this is any. I'm changing the notation slightly here. E is any vector bundle. Right, then this is some, I'm calling this P for the moment, then the cohomology of P is the cohomology of X. Times, extended by this class L, which is the class of O1, right? And what this means is that I do 1, L, L squared, and so on, all the way up to L. This is a n minus 1 bundle. This is this is locally Pn minus 1 times X. So this goes up to n minus 1, right? And this what I've written down here is a basis of this cohomology group over this ring, right? The ring up by pi up a star makes this guy here into a ring over this guy here, right? And just as a module, it's got these guys as bases, right? And then L to the n is given by a relation, right? So this is locally projective n minus 1 space, right? So when I do L to the n, it doesn't make any sense to say, well, it's the hyperplane section of E, because we're really talking, if I took n hyperplane sections, that's the empty set. So this does not make any sense anymore, but I have L to the n minus C1 E of L to the n minus 1 plus C2 E L to the n minus 2 plus, minus, and then Cn of E equals 0. Right, so in particular, if n is 1, sorry, if n is 2, then what I'm getting here is L squared is C1 of E times the fiber times L. Right, and that's this statement. Okay, so anyway, let's do it also more simply from first principles instead of appealing to authority. Right, so let's suppose E is generated by its global sections. Right, so this means I've got E here, and I can take, for example, O plus O, mapping there. So this is two general sections of E. Right, so if E is generated by its global sections, then what this means is I can find one of these E which is good at every point, so I can take two of these by choosing different sections. I can make sections which give a basis at every point. Right. So now if I try, given any point, I can find two elements here which form the basis of it. So if I try to do this globally now, I get O plus O maps to E, maps to some co-kernel. Right, and I can arrange that everywhere locally, x1. So let me call these x1, x2. x1, x2 have rank 2 or rank 1. Right. So this is a little matrix here, a little 1 by 2 matrix. And I can say everywhere it has either rank 2 or rank 1. I can just avoid the zeros. And so the co-kernel is just the number of zeros. Right? But that's the same thing as L squared. Right? So what I'm saying is here I'm taking, if I take L1 to be the divisor of x1, I'm getting this nice section of the bundle here. Right, so this is L1 is in the linear system L1. It's in the linear equivalence class, the divisor L1. Right? And then what I said about these two general sections, I can do this kind of thing. Right, this is L2. And then there are a finite number of places on the base curve where the co-kernel of this map, right, is just one-dimensional vector space at each of these points. At each point of L1 intersect L2. Right, and so there's something here which is obviously the intersection number of the self-intersection L squared, and at the same time it's the co-kernel here. So that's the degree of the bundle E. It's the only, over a curve, it's the only topological invariant of the curve. Okay, so all of that is stuff that, you know, is really very, very elementary. So, you know, if you want to look at Park City lectures, then I have this little discussion of geometrically ruled surfaces. So I have, you know, a surface that looks like this with a map down to C. I have F down to C, and every fiber isomorphic to P1. Right, then this implies that F is of the form F, you know, P C of E for a suitable vector bundle. Right, so this is called Sen's theorem. Right, you know, you think it's, I've been explaining something where the picture is very familiar to you, and so you think it's obvious, but this is, you know, the statement here is that there exists a birational section here. So it's possible to make just from the assumption that F is a non-singular surface, F maps to C has every fiber isomorphic to P1, every scheme-theoretic fiber isomorphic to P1, then it follows that there exists this section. Right? I don't need this result. I'm just pointing out that we're dealing with a little piece of knowledge that's useful in some contexts. Okay, now I'm going to start something which is much more substantial, which is in the direction of the thing I want to prove. Right, and it really only uses this trivial stuff I've said here. Yeah, okay, so if E is not generated by L1, then twist it up a bit and so on and mess around and think about the definition of the degree and you get the same result. It's not a difficult thing. So this is a theorem, and you know, it's easy, but maybe you don't see it immediately when it's given to you as a surprise. Consider curves gamma in FC, irreducible, such that gamma squared is less than 0. Right, so have we ever seen anything like this? Well, we've seen the negative sections of surface scrolls. Right, and so the theorem says, number one, there exists at most one. In other words, if you find one, you'll never find another. And two, gamma in FC with gamma squared negative maps bijectively to C. Right, so the thing I'm saying is this. Here's my surface FC. Here's the base curve C. There's a map down there. Suppose that I've got some curve gamma there. Then it's hard to draw because I want to suggest that it's mapping down 1 to 1. So the map down is 1 to 1, but it's not necessarily, but possibly inseparable. So this is called purely inseparable. Right, so you know, in local coordinates on the curve, it might be x maps to x to the p. That's the in characteristic p. Right, and you can't avoid this. So the conclusion, my conclusion here, is this thing: the curve gamma maps bijectively, and bijectively does not necessarily mean isomorphism if you're in characteristic p. So in characteristic 0. In characteristic 0, gamma to C is separable, and therefore a section, therefore an isomorphism. And C to gamma, the inverse, is a section. Yes. So this map, this map has, you know, some degree, which is p to the n. So this implies here the only way of getting a purely inseparable map is of degree, possibly p to the n, where p is the characteristic. So if the degree is p, if the degree gamma to c is 1, so in other words, if we're in this case, then gamma corresponds to a surjective map. E goes to O gamma, which is OC, with kernel determinant of E, right, with degree of this, degree of determinant of E is minus gamma squared. Right, so this is the beginning of instability for vector bundles. Right, the only way...
Maybe O gamma in the bracket. Why the structural shape of gamma? Section corresponds to quotients, to locally free quotients.
Sorry, I'm not completely following. This is maybe I'm thinking of pi upper star. Maybe I'm thinking of maybe I'm really thinking of O of 1. Right? So I'm taking something which on each fiber P1 is OP1 of 1. Right? And then I'm restricting it to a point gamma on each fiber. And the kernel is a line bundle. So maybe I should write pi upper star there.
Yeah,
is that what you want?
No, I don't understand your sequence, sorry, because phi is rank 2. You have a kernel which is rank 1, so the co-kernel must have generic rank 1.
Yes.
And this is not generic rank 1.
Yes, it does.
Oh, you're restricting everything over C.
Yes, that's right. That's right.
Okay. If you restrict everything over C.
These are. Yeah. Okay. If you want. Yeah. So this is on C.
Okay.
On C, these are rank 1, 2, 1.
Okay. Okay. Now I understand.
Right. But the point is that the assumption that gamma squared is less than 0 says that E has a subbundle of degree positive with quotient of degree 0. Yeah? So this is unstable. The only way, so in other words, if it's possible to find a curve gamma in FC with gamma squared negative, then necessarily the vector bundle is unstable, and the restriction of this O of 1 to the curve OC is the, you know, there's a push down, a push or pull back here, which I think is probably why you're confused. Okay, so how do we prove this? Well, it's very, very elementary. So firstly, so I'm going to use this multiplication table. A squared equals 0, A times L equals 1, and L squared equals D. Degree of E. Yeah? And so, well, you know, any curve gamma is, you know, numerical equivalence, A alpha plus B plus alpha A plus beta B plus beta L. Okay? Gamma squared is 2 alpha beta. So I do alpha squared A squared, right, which I've already done, and then I do 2 alpha beta times A times L. I'm getting this 2A beta beta, and then plus beta squared times L squared. Yeah? And this is beta times 2 alpha plus beta D. And you know, necessarily the beta is positive, right? Because this is supposed to be an effective curve. So an effective curve must meet every fibre in at least 0. And also I'm assuming that gamma is not just a multiple of A, because gamma squared is going to be negative. Right? And so therefore this beta is, therefore this guy here is negative. Right, now suppose I've got 2 of them. Suppose gamma 1 is alpha 1 A plus beta 1 L, and gamma 2 is alpha 2A plus beta 2 L. Right, then 2 alpha 1 plus beta 1 D is less than 0, and also 2 alpha 2 plus beta 2 D is less than 0. Right, so who is gamma 1, gamma 2? Yeah, so it's the same calculation. I do alpha 1 times alpha 2 times A squared, which is nothing, and then I've got alpha 1 times beta 2 plus alpha 2 times beta 1 times, so there's alpha 1 beta 2 plus alpha 2 beta 1 times A times L, which is just 1, and then plus beta 1 beta 2 times D. Yes? Now I'm just going to substitute alpha 1 is less than beta 1D over 2 minus. Yes? And so here I've got, so when I do this, I'm getting here minus beta 1 beta 2 times D over 2. Right, and when I do this term here, I'm going to get exactly the same thing, minus beta 1, beta 2 of D times D over 2. Right, and so I'm getting, what I'm getting here is a term which is less than this, because these are strict inequalities. I'm assuming that gamma squared is strictly less than 0. Right, I'm getting strict inequality here and strict inequality here, and therefore the whole thing is less than 0. Right, and gamma 1 and gamma 2 are supposed to be irreducible curves. So, you know, this looks like magic, and, you know, maybe it is, I don't know. It's the property of this P1 bundle being unstable, having this negative section, is a very, very strong property. So this, the vector bundle over a curve, if it's unstable, the instability structure is extremely strongly, uniquely defined. Right, so therefore, gamma 1, gamma 2 negative, and therefore gamma 1 equals gamma 2, because I'm assuming they're irreducible. Yes? So for the second part, for part 2, I'm just going to say this. So here's my gamma, right? Let's think of the gamma as being hanging in the air there, lying over C. Right? There's an extension of function fields. K of C included in K of gamma. Yes? So this has a splitting field. It has a splitting field, some L. So the thing I'm thinking about really is that this, if I take the generic point of the curve here, right, then I get this non-algebraically closed field. And what I've got here is one parameter and this is a single polynomial equation. Single polynomial equation, f of t equals 0 with f with coefficients in this field Kc.
Maybe call the splitting field in another way because M is already...
I'm sorry.
No, of course it's
Yes, okay. So it's, what do you want me to call it? Capital K?
Yeah, that's you want.
Yes. So, the property of a splitting field is that this polynomial now splits completely into factors, and all the factors are conjugate under a group of automorphisms of the field. Of course, I've got to be a little bit careful. I can't say Galois group because the field extension might be inseparable, right? So right now C primed, or C twiddles, equals the model, the integral closure of C in K. So I'm just going to take this same picture and pull it back to C. So now here I've got my gamma contained in P over C of this bundle E. Here's the base curve C. Right, and I'm going to make an extension of the base field, extension of the base curve. So C primed here. Right, and by construction, this now has gamma 1, gamma 2, gamma 3. So then make the pullback C primed. So this is, of course, P over C primed of the bundle pi upper star of E. This map's pi. So maybe this map is psi. Right? And so this is the normalized fiber product. I don't need normalized. It's the fiber product C cross over C prime cross over C with P of E. Yes? And so now if I go to the generic point of C primed, then this polynomial f has now split into different roots. So the point is that all the fibers, all the pullbacks of gamma are conjugate under automorphisms. Automorphisms of C primed.
You cannot say this thing because you don't know if the extension is separable.
The extension is not separable.
So you cannot say this thing.
I can say this, see?
You can say.
I can say, yes.
Why?
Because I taught a course in Galois theory. So look, if I've got a field extension, I can make an extension of the field where this polynomial has at least one root. And then I can continue. Look, a Galois extension is an extension which is normal and separable. Right? I'm not insisting on separable, I'm just taking normal. You can make this, you can make this, first of all I make a section. So that section is necessary, if the whole thing, if gamma to C is inseparable, then any section is, any field in extension here is necessarily inseparable. Right? But if I take one root of this polynomial f defined over this field, and any other root defined over this field, then there is an automorphism in the field that takes one to the other.
Yeah.
We don't need separable.
Yeah.
I'm not saying the extension is separable.
Yeah. The only thing is that if it is not separable, the number of distinct roots is less in general of the degree of the section.
Of course, I agree with that. I agree with that. But this C prime to C.
Okay.
So in any case, the point is that now if I take, so think of this. I'm going to call this map psi as well by abuse. So if I do psi upper star of gamma, then this squared is negative. On the other hand, he's equal to gamma 1 plus gamma 2 plus all the different components there squared. Possibly with multiplicity, I don't care. I mean, they'll all be the same, right? And all the gamma I squared equals all the other gamma j squared, right? Because they're symmetric. So of course, the way to do this is first make the pullback by gamma to C. Right? First make the pullback by gamma to C. Then I have some new surface. The pullback contains at least one curve because it contains the section gamma. Right? And then if it's not the splitting field yet, continue to make the splitting field. This is I'm not, maybe haven't said it I've said it slightly clumsily, but this is a very elementary argument. Right? So what's the conclusion here? The conclusion here is that gamma to C must be bijective. Maybe I could start off by making, maybe I'd make people happier if I start off by making the inseparable extension. I take the separable, maybe what you said is right. I take the separable closure of C in gamma, of the field C and Kc and K gamma. Right? And then from that moment onwards, the extension is separable. I think that's right. Anyway, you see what's happening. So let's just go to characteristic P. Let's give ourselves an easy time. Right? I've got this surface here with this. I've got this possibly multi-section over gamma. Right? I can make the splitting. I can find a covering here. I can find a curve C primed now, which is Galois over C. Right? Make the pullback by that. Then certainly this thing has split into all the different conjugates of one section. Right? And they're all conjugates, so they all have the same gamma squared. On the other hand, at least one of them has to be negative, and so therefore they're all negative, and that contradicts the first. So this is because all the gamma I are equal, and at least one of them is less than 0, and therefore, they're all less than 0. So there's only one of them. Sounds crazy. So, you know, this is... So, you know, the thing I'm guarding against in this, when I say separable, it is possible to have a vector bundle which is stable over a curve, but where when you make the pullback, for example, by Frobenius or some other inseparable map, some power of the Frobenius map, becomes inseparable. These are called tango curves, or tango Renault curves. I don't actually know an example in my head, but you know, they appear in various counterexamples, various constructions of characteristic P-algebraic geometry. Right. So if we sort of ignore that point, in other words, if we go to characteristic 0, then this point just completely disappears. Right. So the only way to get gamma in FC with gamma squared less than 0 is for E to be unstable. You know, or Frobenius pullback. In characteristic P. But anyway, if we think just characteristic 0, then we really don't need this. In any case, the theorem I'm aiming for, the Bogomolov instability theorem, is false in characteristic P. It's not true. Okay? So the next result, you know, this is I'm really now sort of this is the you know, the result I said is about these rule surfaces, and you can think all this is very trivial mathematics, something that everybody knows, just rank 2 vector bundles over a curve, right? But this theorem I just stated is really this theorem I've just treated is really very substantial. You know, surprisingly simple, surprisingly trivial, but also surprisingly effective. So the next thing is sort of an extension of that. So suppose, now I've got FC as before, so this is P over C of vector bundle E. Oh, I'm sorry, I think I had before E. Okay? And I've got this bundle B. So this is O of 2, OP of 2, OP of E of 2, tensor determinant E to the minus 1. So this B squared is 0. Right, because it's so why is this? So you know, this is just this multiplication table. A squared equals 0, A times L equals 1, and L squared equals D. Right, I've got the vector bundle, which is, so D is the degree of E. Right, so the vector bundle I've got here is 2L minus D times A. Right, so this square is 4L squared minus, so the cross term here is 4 times D times A times L, and then the A squared term vanishes. Right, so this is 4D minus 4D. right, times B. I take the linear system corresponding to this divisor B. This is a base locus, fixed locus. What should I write? A fixed locus. Plus, suppose it's a fixed locus plus a birational linear system, a linear system, an effective. I want a mobile linear system, M, mobile linear system with m squared positive. Okay, then, and maybe, so let me just assume characteristic 0 for the moment. So let's assume characteristic 0. I don't think it's important, but so let me just say it anyway. Then then FC contains a curve gamma with gamma squared less than 0. Gamma is a section, and every section, and the right thing to say is now n gamma is contained in the base locus of NB. This is again just intersection numbers. There's nothing, absolutely nothing happening here. So look, here's my situation. I've got this B, I've got this NB. Right? On the one hand, his degree on the fibre is 2n. Right? On the other hand, b squared equals 0. But I'm assuming, maybe I need a name for that original fixed part. Right? Let me call the fixed locus G. I don't want to say F because I've already got an F. Right? So I look at NB. Right? This is G plus M. And the M squared, the M is mobile. Right, so I can assume that the M is irreducible, or at least it's Nef, and M squared is positive. Right, so the left-hand side, if I take the square of the left-hand side, NB all squared, this is certainly 0. Right, but anyway, this is G squared plus 2GM plus M squared. And these are effective divisors, so this is greater than or equal to 0 because the M is mobile, and this is greater than 0. And so therefore, G squared is less than 0. And so therefore, FC contains a gamma with gamma squared less than 0. Right? However, in my assumption, in the stuff I'm assuming, this because I'm assuming separable now, this gamma is a section. I'm sorry?
You wrote FC contains a gamma. You mean G contains a gamma. FC is
Yeah. I mean, obviously, FC contains some section with gamma squared less than 0. So I'm in the conclusions. Of course, gamma is in G.
Okay.
Right. But I want to see that actually n gamma is in G. So in other words, these, I've got this linear system here, and the linear system has got degree 2n over the base, and I say it's got a fixed part here of multiplicity at least n. Right? So this is instability. So how do we prove this? Maybe I can leave it as an exercise and we can break up for coffee. C will be a general curve on a higher dimensional variety, and the conclusion will be that if you assume that this B is, this B is just the relative tangent bundle. Relative tangent bundle of a P1 fibration. So he's a certain line bundle. On the other hand, he's a line bundle with the property that his square, restricted to every one of the surfaces over every one of these curves, is 0. So if he has lots of sections, or even if he has just a few too many sections, then he must have this negative section of multiplicity at least n. Right? And that's what Bogomolov instability says. Okay, so I'm going to rest for 15